Hi everyone, and welcome to another video in this series of videos going through some past exam questions on redox titrations. This is the second out of 4 videos focusing on redox titrations involving iodine and thiosulfate ions. Okay, and again, I'm going to start off every video, it seems the same way because all these questions are the same. Again, we've given us a massive chunk of text that we've got to read through, and then they've given us a massive blank space that we need to write our answer into. Okay, so these, as I've said before, these questions do all look kind of the same. Similarly, again, I'm not going to bother to read this. I'm going to go and look at the question first and see whether I need to, because I'm just going to boggle my mind reading through all of that. I want to know what I'm looking for. So first thing we've got here says complete the electron configuration of copper. Okay, so this is really a transition metals question. So we might not have covered this. By the time you're doing redox titrations, you might not have done transition metals yet. But I'll go through this anyway. So copper, let's just find copper on our periodic table. So copper is here. If we look where this is, we're in period 1, period 2, we're in period 4. This is the D block, isn't it, in the middle? So copper's electron configuration should finish up with 3D. Remember, even though it's in period 4, this is actually 3D, isn't it? And it's 1 before the end of the 3D, so it should be 3D9. Okay, so let's just write out the electron configuration of normal copper first. So it would be 1s2, 2s2, and then we'll think about what's going on in these things. 2p6, we're going up to 3d9, we said. 3s2, 3p6. We do 4s first, don't we? 4s2, 3d9 would be copper, but, and this is why they've specifically chosen copper, copper is an exception to this rule. We do fill the 4s first, but copper's electron configuration isn't 4s2, 3d9, it's actually 4s1, 3d10. So you need to be a little bit careful with that one. It's a bit of an exception to the rule. So that would be copper. So then we need to think about what's going on in these two compounds. Let's have a look. What is this thing? Let's see if this looks weird. Try and work out what this is. It does give us a clue up here. So it says they prepared this thing, whatever it is, by reacting a copper compound with aqueous methanoic acid. Okay. So this is copper methanoate. Okay, this HCOO, that is your ion from methanoic acid. It's the methanoate ion. That's what that is. And there are 2 of them, look. So that means that the copper must be copper 2+. Because it's reacting with 2 of those negative ions. So therefore here, if we've got copper 2+, we're going to take off 2 electrons from this end. But remember, the 4s fills up first, but it also empties out first. So we're going to take off the 4s1, and then we're going to go down to 3d9. Okay, so we 1s2, 2s2, 2p6, 3s2, 3p6. 4s1 is going to go, and it's going to be 3d9. Okay. And then copper 1 iodide. So this is obviously copper in a +1 oxidation state. This was copper 2+, wasn't it? So it's going to have 1 more electron than this. So it's only going to have lost 1 electron from this lot, and it's going to lose the 4s first. Okay. So this would be almost the same as what we've got, but it's going to be 3d10. Okay, part B says, choose a suitable copper compound for step 1 and write the full equation for the reaction that would take place. Okay, so what was step 1? So this was making this copper methanoate by reacting a copper compound with aqueous methanoic acid. Okay, so we can have any copper compound we like. Okay, so we're going to have methanoic acid though, which is going to be this, but with an H on the end. There's our methanoic acid. What's going to react with an acid or an acid and a base? So we'll have, let's have copper oxide. You could have copper carbonate, that would work. Copper hydroxide, that would be fine. I'm going to go with copper oxide here, but any of those should work. And write the full equation. Okay, so it's going to react, it's going to make the product here. And if we've got an acid, copper oxide, a base, it's going to make a salt and it's going to make water, right? And then we've got 2 of this ion, so we're going to have a 2 here. And then we lose the 2 hydrogens and the 1 oxygen to go make the water. Okay. We don't need state symbols, so that's fine. Right, part C. Write an ionic equation including state symbols this time. So, I mean, sneaky. We don't need state symbols. Oh, now we do. Horrible. For the reaction in step 3. Right, step 3, what's going on? Using a pipette, they added 25 centimeters cubed of this solution. Okay, I'm going to have to read that. Followed by an excess of potassium. Okay, so it's something reacting with potassium iodide. What is it? Okay, it's just a solution of this thing. Okay. So what's going to happen here? Oh, it tells us here, look, the copper 2 plus ions react to form a precipitate of copper 1 iodide and iodine. In this reaction, 2 moles of copper form 1 mole of iodine. Oh, that's nice. We're not even going to have to work it out. Okay, perhaps that's why they're being horrible, because they've been quite nice to us up here. So copper 2 plus ions react. Okay, so we've got copper 2 plus ions. We do need the state symbols this time. Reacts to form a precipitate of copper 1 iodide. Okay, so it's just reacting with iodide ions then, isn't it? Because it was from potassium iodide. But the potassium's always soluble. That's going to cancel out. So it's going to react with the iodide ions. And it makes a precipitate of copper 1 iodide. That's going to be Cu(I). This iodide's obviously 1 minus. So copper 1 is going to be Cu plus. As that's a precipitate, it says. And it makes iodine aqueous. And we've seen this reaction before, haven't we? This was in a previous video. 2 moles of copper, it even tells us 2 moles of copper makes 1 mole of iodine. Well, that's very nice, isn't it? All right, I'll do that then. So therefore there's going to be a 2 there. And then I've got 4 iodine, so that's going to have to be a 4. Okay. And so you probably will get familiar with that reaction because it comes up quite a bit. Right, and then the last bit here, in step 4, the student adds a solution to observe the end point. Okay, what was step 4? This was a titration, titrating the iodine against the sodium thiosulfate. Yeah, hopefully we're familiar with this. So they added some sort of solution to observe the end point. Okay, so we should hopefully be aware of this. When we want to do an iodine thiosulfate titration, we want to use starch. That's going to show the presence of the iodine. State the colour change at the end point. Well, starch, when it reacts with iodine, goes a blue or black colour. But we just need to be careful here. Which way round is this? You can see that iodine is the reactant. Okay, so we're going to have iodine there at the start and not at the end. So it's going to be blue or black to start with. And it's going to go to colourless. Okay, the iodide ions don't react with starch at all. It's only iodine. Okay, so those were all the little bits. Then we've got the big blank space. I've got a 5-mark question here. What are they actually asking us to do? Determine the value of X. So it's a water of crystallization thing, really. Okay, so right, let's have a look. Let's go back to all this information. And if you watch the previous video, I'm going to work through this in a very similar way. And the first thing I'm going to do is find all the numbers. So we've got a concentration here and we've got a volume. That's the same concentration, so let's do that again. Any more numbers? We've got 25 centimeters cubed here. We've got, oh, here we go, look. You start to see the same thing. Oh, look, we've got a 250 and a 25. Right, we know what we're going to have to do there, don't we? We've seen that before. And we've got a mass here. Okay, so we're going to start with this, right? Concentration and volume like we did in the previous one. So we're going to do 23.5 divided by 1,000. Get that into decimeters cubed. I'm going to multiply that by the concentration, which was 0.042. Right, let's do this. 23.5 divided by, 23.5 divided by 1,000 times 0.042. 9.87 times 10 to the minus 4. Right, what have we just calculated? Thiosulfate, I would assume. Yes, thiosulfate. It's usually the same way with these questions, right? It's kind of predictable. You work out the thiosulfate. What we're going to do now is we're going to use the ratio, right? This is literally exactly the same pattern as the previous video in this series. So we're going to use the equation here to look at the ratio. It's a 2-to-1 ratio to get to the iodine. So we're going to have to divide by 2. So the ratio of iodine to thiosulfate is 1 to 2. So we have 9.87 times 10 to the minus 4 over 2. So we'll take that, we'll divide it by 2. 4.935 times 10 to the minus 4 moles of the iodine. Okay, right, so that's our iodine. If you remember, we're working our way back up the page basically. So we've got to our iodine. So we got this. Where did this iodine came from? Came from there. Okay. So what do we know about this iodine? This came from 2 moles of copper at a 2-to-1 ratio here. And again, we want to get back to the copper, don't we? Because we're trying to find out about this thing and about how many waters of crystallization it's got. So we want to know about copper. So we're going to do 1 to 2 ratio to get back to the copper. Okay. This is why I thought they were being nice to us when we were writing the equation. The reason they've written this here is even if you've messed this up here, you could still be able to do the calculation question because they've told you the ratio there. That's why they've put it there. Right, but it's a 1 to 2 ratio, so we're going to multiply by 2. So we're going back to the same number. Can you see how this is exactly the same as the previous video? Hopefully you watched the previous video, otherwise me keep saying that's not going to mean anything to you. But the iodine to the copper 2 plus ratio was 1 to 2 again. So this is the iodine though, so we need to times it by 2. So we're back to this number again. Of the copper 2 plus. So I'm just going to times up by 2 and get back to that. Right, what do we do next? It's exactly the same again. We've now got this copper solution, which is this. So now we're doing the next bit, which is we're going back to our 250. So this is exactly the same again as we've done before. We need to times it by 10 to get back to the original solution. So that was in 25 centimeters cubed. So it's going to be 9.87 times 10 to the minus 3 moles of copper in 250. Right, and then what have we then got? We've got the mass. Now we need to think a little bit now about what we actually want to do. How are we going to work out what this thing is? Well, to work out how many waters, we want to know the formula mass. If we know the formula mass of it, then what we can do is take away the formula mass of the anhydrous part and be left with the water. So what we're going to do is we're going to use the mass here and the number of moles that we've already worked out to find the relative formula mass. So we're going to do this mass here divided by the number of moles. So we're going to do 2.226 grams divided by this number of moles. So I need to times that by 10, and I need to do 2.26 divided by that. Oh, hang on, nearly got that wrong. 226, that is right, isn't it? Yeah. 2.226 divided by that answer. So we get 225.5 grams per mole. Okay, so that is our formula mass of the hydrated version. So that is the formula mass of this whole thing. What we can now do is if we work out the formula mass of this anhydrous part and take that away, that'll give us the formula mass of the water. Okay. So if we do the MR of the copper with its 2 copper methanoate anhydrous, that's going to be 63.5 plus 2 lots of 1 plus 12 plus 16 plus 16. So what have we got? We've got 32 plus 13 times 2 plus 63.5 is 153.5. So then we're going to take it away. 222.5. What am I doing? 225.5 minus 153.5. So that comes out as 72. That's nice. So then that then is the XH2O part. So what we now need to do is work out the formula mass of water. 1 times 2 plus 16, which is 18. And then we can divide this, which comes out as 4. I'll prove that to you in case you don't believe me. So that's going to tell us that we've got 4 waters of crystallization. So we can just write this out. Let's just make this super clear for the examiner. We're going to write X equals 4, and then we can write out CuHCOO2.4 H2O. Okay.